We're going to talk about pointers in this tutorial. If you want to follow along with the slides, you can start off on our home page and go to tutorials for week 5, and it's the pointers tutorial. Now, a lot of people would say when you're learning a computing language, and C is one of the really foundational computing program languages to learn to start with, because it's compared to modern languages, it's relatively low level. It gives you a lot of power. Some of that power can be annoying sometimes, and more modern languages take you closer to human language. One example of a feature in C that people find especially difficult to comprehend and awkward when you're first learning it is this concept of pointers. But this is one of the maybe the most important concept that we're going to cover in this module. It also is traditionally viewed as difficult and annoying by people who are learning, but you have to take my word for it. I can't emphasize this strongly enough that the investment in wrapping your head around pointers, how to use them, is once you overcome the learning curve just a little bit, that annoyance and confusion will go away, and it's worth doing it. In fact, I would go even further to say that if you're in any way serious about doing this kind of work, it's essential to do it. Just get over it. It may require you to watch the lecture, go through the tutorial notes, look at this tutorial video, and possibly even do a little experimentation in your own code. That would be extremely useful for everybody, even people who have used pointers before. You could read a little bit outside of the module materials as well if you're struggling, and do let us know how you're getting on in the Discord channel. All right, so what this tutorial is going to do is just go through the concept of a pointer, give you some more examples in a little bit more detail than we did in the either the lecture video or the lecture notes. Okay, so what is a pointer? Pointers provide a way to pass data between functions. Up to this point, when we've declared variables and used variables inside functions, we've done it by the value of the variable. And when we pass data by value, we're really only working with a copy of the data. And that's the way we can start to think about it. Now, pointers, instead, they allow us to directly pass the variable itself, because we're accessing the address in memory of where the data live. And by accessing that address, we can directly change values that are stored at that address. So in other words, the impact this has in your coding practice is that if you use pointers and change data in one function, it can impact what happens in a different function with respect to that variable. And without pointers, that's not possible in C. And we're actually going to step back just a little bit and make a few things explicit about memory. If you have a computer, even your phone works like this. But on a regular desktop, we think of things in terms of memory. We actually have two kinds of memory, and we want to make sure that we understand the distinction between them. The files that we store for the long term live either on a hard disk drive, an HDD, or modern computers and laptops have solid state drives, SSDs. If you don't know the difference of that, the hard drive is maybe it's a bit old-fashioned. They're still in wide use, but they have magnetic platters that spin and then a reading head that read the platters. Solid-state drives are memory based on chips that the data stays even when you turn your computer off. Both of these kinds of disk drives are very common in modern computers. Well, the disk drives are just storage. We don't actually directly work there when we're doing stuff on the computer. And when we manipulate data, and it might be reading a file, creating a Word document, or running a C program or something that we wrote, we we have to read the data. And if it involves data we stored on our hard disk drive, we read it and store it so that we can work with it in something called RAM, random access memory. And so we have to move the data there to work on it. And memory is basically just a huge array of individual components that are in 8-bit wide bytes, okay, arranged in various configurations. And if you have a really old computer, you might have 512 megabytes. Nobody really has computers that they use day to day these days that are like this. Even your phones. I'd even wager, I'd be surprised if anybody even had a phone with as few as 512 megabytes of memory, but it is possible. It'd be more typical to have more memory than these increments. A typical modern laptop would have, at minimum, if it was an older laptop, 4 gigabytes, more typically 8 these days. And if you have a desktop and you're doing work with data and programming and computers, it's more likely that you'd have 8 or even 16 or even a bit more gigabytes of RAM. Well, why are we talking about memory? Well, when we're talking about storage of data types, we know that different data types require storage space for different kinds of memory. We've covered this in past lectures and past tutorials quite a bit. When we look at the data type of the int, we can see that it takes up 4 bytes of memory. And likewise, we've talked about individual chars take up just a single byte for a single letter or alphanumeric character. Floating point variable takes up 4 bytes. A double is a high precision with a lot of decimal accuracy. Floating point or decimal number takes up 8, twice as many. A long is a very, very large integer, so that takes up 8 bytes. And then we have the string. Now, how much memory does a string take up? Well, we'll come back to that at the end of the slides. So we've presented this metaphor of memory being a big array of bite-sized cells, BYTE, not BITE. And when we've been talking about arrays, we've talked about them being useful not only for the storage of information, but for random access to data stored in arrays, such that if you have a big array, we can access individual elements of the array by exploiting the address, the index of where the data we specifically want is. And that brings us to this idea of addresses that we've talked about quite a lot up to now. We can visualize an array like this. It's a series of, we can metaphorize them as a series of boxes or houses on a street, and each of those boxes has a number, or if they are houses, they have a street address. And the indexes, we know the index starts at 0. And for these 20 bytes of storage space, goes up to 19, 0 to 19. And, we could store a char variable type. Maybe we want to store a char called C, and in C we initialize it to have a capital H. All right, and we would initialize that with code that looks like this. The computer would find a space in memory and allocate that memory if we did a declaration like this. And likewise, if we were to store an int, we know that's 4 bytes. The computer would allocate some other little bit of space here, starting at address index 8. And we've initialized this to 65. We called it speed limit. Of course, because it's 4 bytes, the computer thinks of that as a whole chunk and would store this as a contiguous chunk of memory to store our int character when we when we did it. And of course, it would contain at index 8 the integer 65. Well, let's look a little deeper at what's actually going on. If we actually look into memory, we know a byte is 8 bits of information, and a large capital H would be converted to binary for storage, and likewise the integer would be converted to binary, and it would actually be stored in binary format. Would it be stored exactly like this? Well, it turns out that that it doesn't. It's a little more complicated than that. We're not going to talk about that in this class, but you know, the byte actually is stored as 4 individual. The int rather is stored in 4 bytes, and the 4 bytes are actually represented separately by the computer. The beginning, you know, here at 8, and the ending, the business end for the number 65 down here in 11. But you know, this is a simplification, and we're not going to go into any details in this module. It's not relevant to us. But if you're interested in this kind of thing, you could read up a little bit on little and big Indianness. You know, I'll leave that up to you if you're interested. All right, so we've got our data stored here. What if we wanted to add a character string, and we wanted to call it, you know, Lloyd, somebody's surname? The computer might pick another space. Now, there's one thing that I want to point out here is that the computer seems to have picked an arbitrary space. Why didn't it start at 0? Well, it may be that 0 is being used for something else on our system, something else that's going on at the same time. So the computer's picked a space that's appropriate. And another thing is, why didn't for 65 it pick the next available space? Well, it may be that the next available space is used for something, or maybe that there is an efficiency algorithm that has something to do with how memory is allocated. And again, that's beyond the scope of this course. But here, Lloyd is picked to be end-to-end with our int speed limit, no problem. And this is what it would look like, right? Or would it? No. What are we missing from Lloyd? We know character strings have to be specified in a particular way. Well, we need that null character at the end, a \0, to indicate the end of the character string, because we know that character strings, the address is allocated from the first, from the beginning of the string itself, and then we need an indicator for the end of the string. So, you know, the string length is determined, the memory footprint for a string is determined by the string length, and the boundaries are the first character and the null character. Now, I've converted the indices 0 to 19, these 20 addresses, to hexadecimal, because that is the name of the game when we're using pointers, and that's how they're actually stored in computer memory. So we've got the hex, you know, 0x indicates that these are pointers at the beginning of every one. 0 is the 0 space for our hexadecimal pointer. F is the 15th space, or it's the 16th character, but in the index 0 to 15. And then we've added the extra ones on here to go up to 19. Okay, well, there's one critical thing to remember. Even though pointers are confusing when you're first starting this stuff, and thinking about them is counterintuitive sometimes, we have to remember pointers are just addresses. It's just an address of where the data live. That's it. There's nothing more to it. Okay, so as we start to work with pointers, maybe a pictorial image in your mind will help. So let's go through this. That might be a different way to think about pointers. So let's say that we initialize an integer called k, and you can visualize in your mind. I know we have been visualizing that grid system and boxes in a memory grid to visualize this previously, but maybe think of a different way. Let's just say that we've set aside some memory. We don't even have to think in any more detail than that. And by virtue of declaring it as an integer, maybe the color of that space that we've set aside is green. Okay, so we know that it's an integer because it's green. And then we can assign a value to that variable k, and maybe here we put 5 in it, and that's like putting 5 into this space, and boom, 5 pops into the space. Well, now we have a pointer to k that we've declared, and that sets aside a different amount of space. It's still green, but notice the shading is a bit different, and this designates that it's a pointer that's going to go here, and we know that this is it's going to hold the address of k. And so the address could be in hexadecimal, would be in hexadecimal. We've got some big number here. That's the address of k that is currently taking on the value of 5. Okay, so what we do now is we just envision this connection between the pointer and the space that we've set aside for k currently taking on the value of 5. Well, think of a pointer. We've defined it in several ways, but think of it itself as a data item whose value is a memory address, and the type of which, the data type, describes the data type located at that memory address. And as such, these pointers allow data structures, data variables, to be shared amongst different functions. This is the power of pointers. This is the reason why pointers. Okay, so pointers make a computer environment and sharing of information between functions more like the real world. And I have this little note here. There's this notebook analogy. It's like this. What if I had a notebook myself that I took notes in a module for, and it's filled with my notes, and I went to somebody else and I said, hey Bobby, take my notebook and can you clean it up and remove the errors and update it for me with the latest course information? So without pointers, what Bobby might do is he might take that notebook, make a photocopy of every page, so make a copy of it, change every page of my journal to update it, and then hand me back those photocopied pages. And then it would be up to me. Do I want to update my original journal? Well, that creates extra work. As opposed to, if we use pointers, the journal analogy would be like, Bobby, update my notebook and remove the errors. Here's my notebook. Just directly do it. Here, this is where my notebook is. Just directly update it. And taking the actual notebook and updating the information in it. That is like how pointers work. All right, so a little unique aside here about pointers is that the basic kind of pointer that's available for every pointer call is what is known as a null pointer. And we might guess that this pointer points to nothing, and this can actually come in handy. We'll talk a little bit about that. So when you create a pointer, you don't set a value immediately. What you need to do is, for best practice, that is, you should set the value of that pointer to null. All right. The reason for that is if you don't set it to null, it might be set to an address value arbitrarily that contains garbage, and you don't want that. And you can accidentally then use that pointer. It could also be used maliciously. We're talking sort of, beyond the typical use cases of this module. So we're thinking ahead. In other words, because of several reasons, it's best practice to set and initialize that value of a pointer when you declare it to be null. And, you can have checks where you check whether the value of a pointer is null using, the binary logical operator equal. Another way to create a pointer is to just extract the address of an already existing variable. And we do that with the ampersand operator, like we talked about in lecture and in the notes if you went through those. For example, if x is an int, then ampersand x is a pointer to an int whose value is the address of x. And likewise, for an array, this is another little special case that we think of a little bit differently. If array is an array of doubles, then the ampersand array square bracket I, this is a pointer to a double whose value is the address of the ith element of array, whatever the value of I is. And we can think of the name of an array variable is actually just a pointer to the first element in the array. That's actually how they're defined and they function in C. And so in a sense, you've been working with pointers all along when you worked with arrays. And this is a new way to think about that. All right, so the main purpose of using pointers in the first place is to allow us to modify or inspect the contents of the location to which it points. And we do this with the dereferencing pointer. So maybe we have a pointer to a char. Maybe we call this PC. Then the asterisk PC is it's the data that lives at the memory address stored inside the variable PC. All right, so used in this context, we referred to this in lecture. The asterisk is known as the dereference operator, and it goes to that reference, accesses the data at that memory location, and then you can do what you want with it. You can change it, you can update it, you can copy it to another location. And this is just like a visit to your neighbor. Having their address isn't enough. You need to actually go to the address, and then you can do something like, help copy the journal. So, well, what happens if you try to dereference a pointer whose value is null? Pause the video and think about what might happen. Well, there's an error and a crash probably, and there's a specific name for this referred to as a segmentation fault. We think of crashes usually as being a bad thing, but actually we want segmentation faults to happen. This is actually the desired good behavior that is underscored by the best practice of setting pointers when you initialize them to the null value. So this defends against manipulation of pointers that might be unknown. So hackers, but also accidental manipulation of them. And so that's why best practice is to set your pointers to null. All right, so int asterisk p. The value of p here is an address. So here p is a pointer. Notice the spacing. We talked a little bit about this in lecture. The spacing of where you put the class declaration, the asterisk, and the variable is actually flexible in C. This is not good. In my opinion, flexibility like this shouldn't be permitted. Users shouldn't be allowed to use what just prefers to them. But there are some conventions, and we're going to talk about that in the next couple of slides. So for now, even though we talked about this in lecture, that the typical syntax would be int space asterisk p with no space between asterisk and p. Here we have int asterisk space p semicolon. Just ignore that for now. So here we're dereferencing the value contained in the variable p using that pointer operator. And if we do that, we'll find that at that location is stored a variable that is of class int. Okay, so this is one more annoying thing. This is, again, another exception that probably is a flaw in the C programming language. It's been, it doesn't exist in subsequent languages, but a nice thing that people use if you just look at this code is you can initialize an int. For now, let's pretend that asterisk isn't there. You could initialize 3 variables by declaring int and then naming the variable separated by commas, and it would initialize 3 ints. And because of that, you might expect the dereferencing operator to declare 3 star int type variables. So one pointer called px, a pointer called py, and a pointer called pz. But actually, it doesn't work like that. To do that, we'd need to invoke the asterisk each time with each variable. And, here's just an example. This is all correct, and it would be correct if the asterisk touched the PA as well. And the green line here, the bottom line here, would initialize 3 dereference variables of type int. Okay, so we're back to this table about the storage of different data types, and we're going to unveil what happens with string. So maybe we have a char type here. It turns out we, by default, we allocate either 4 or 8 bytes. And I'm not going to go into this with any detail, but depends whether you're using a 64-bit or a 32-bit operating system. That's refers to how memory is allocated for when there's uncertainty in how much memory is needed. So 64 bits use 8 bytes, and 32 bits use 4 bytes of data for char kind of variables, for string type variables, char star. So we have different types here, char, int, float, doubles, etc. And also we can, have custom definitions. All right, so what is happening here when we exploit these variables and make use of the power that's contained with them? Well, if we make a call with the dereference operator on PK, and we set the value that's at the address for PK to 35, it's going to update the value of 5 to 35 in the K box. If we declare a new variable, int m, we're going to make a new box. It's green because it's an int. And we're going to set that value to 4. So 4 is going to be contained in that box. And then we're going to set the address of PK to the address with the address operator, the ampersand m. What's going to happen here? Well, it's going to actually then, PK is going to point to the address where m is. And this is the magic and power of pointers. I've gone through this in more detail than we did in the lecture. This is one of the things that people find confusing and even frustrating. You've got to embrace it. You've got to grasp the nettle, as they say in the UK, when there's something that you don't find pleasant, but you just have to get on with it. And if you have any problems, we can talk about it. And that's all that I have to say about that.